Hi everyone, welcome back. In this video, we will discuss the top Spring Boot Microservices interview questions and answers for candidates with 3 to 5 years of experience. I am going to explain each question to the point and you can answer the same way in the interview. Let's get started. What are the core principles of microservices architecture and how does Spring Boot support them? Microservices architecture is based on building applications as a collection of small independent services. Each service is responsible for a specific business capability and can be developed, deployed, and scaled independently. The core principles include loose coupling, high cohesion, independent deployment, and decentralized data management. Services communicate with each other using lightweight mechanisms such as HTTP or messaging. Spring Boot supports microservices by reducing configuration overhead and enabling fast service development. Each microservice can be built as a standalone Spring Boot application with its own embedded server. Spring Boot encourages separation of concerns by clearly defining controllers, services, and data layers. This aligns well with microservices, where each service owns its logic and data. Configuration externalization allows the same service to run in multiple environments without code changes. Spring Boot also integrates easily with cloud and container platforms, which are commonly used with microservices. In interviews, experienced developers are expected to explain that microservices are not just about splitting code. They are about designing services that are independent, resilient, and aligned with business domains. Spring Boot acts as an enabler, not the architecture itself. Next question. How do Spring Boot microservices handle service discovery and why is it required? In a microservices architecture, services are dynamic. Instances are created, destroyed, or scaled frequently. Because of this, hard coding service addresses is not practical. Service discovery solves this problem by allowing services to find each other dynamically at runtime. Each service registers itself when it starts and removes itself when it stops. Other services query the registry to locate available instances. Spring Boot microservices rely on service discovery to enable loose coupling between services. A service does not need to know where another service is running. It only needs to know the service name. Service discovery also supports load balancing. When multiple instances of a service are available, requests can be distributed across them automatically. Without service discovery, microservices become tightly coupled and difficult to scale or maintain. Failures also become harder to handle. In interviews, experienced developers are expected to explain why service discovery is essential in distributed systems, how it enables scalability, and how it prevents configuration-related failures in real-world microservices deployments. Next question. How do you handle inter-service communication in Spring Boot microservices? Inter-service communication is a critical part of microservices architecture. Services need to exchange data to complete business operations. Spring Boot microservices typically communicate in two ways, synchronous and asynchronous. Synchronous communication is commonly done using HTTP-based APIs, where one service waits for a response from another. Asynchronous communication is used when services do not need an immediate response. Messages or events are sent, and services process them independently. This approach improves scalability and reduces tight coupling. In real systems, network failures and latency are unavoidable. Therefore, communication must include timeouts, retries, and fallback mechanisms. Without these, a slow or failing service can cause a chain reaction and bring down the system. Choosing the right communication style depends on business requirements. Overusing synchronous calls can reduce system resilience, while asynchronous communication adds complexity. In interviews, experienced developers are expected to explain communication patterns, trade-offs, and how failures are handled gracefully in Spring Boot microservices. Next question, how do Spring Boot microservices handle data management and database design? In microservices architecture, each service should own its data. Sharing a single database across multiple services creates tight coupling and defeats the purpose of microservices. Spring Boot microservices follow the principle of decentralized data management. Each service has its own database or schema, which allows independent evolution and deployment. This design improves scalability and fault isolation. If one service's database is slow or unavailable, other services are not directly affected. However, managing data across services introduces challenges. Transactions across multiple services are difficult. Instead of traditional distributed transactions, systems rely on eventual consistency. Data duplication is common in microservices. Services may store copies of data needed for their operations. This improves performance but requires careful synchronization. In interviews, experienced developers are expected to explain why database per service is important, how consistency is handled, and what trade-offs exist when designing data models for Spring Boot microservices. Next, how do you design microservices for fault tolerance and resilience in Spring Boot? Fault tolerance is critical in microservices because failures are inevitable in distributed systems. Services can fail due to network issues, high load, or infrastructure problems. Spring Boot microservices must be designed to handle these failures gracefully. A service should not crash or block indefinitely when another service is unavailable. Timeouts prevent services from waiting forever. Retries help recover from temporary failures. Circuit breakers stop repeated calls to a failing service and allow it time to recover. Bulkhead patterns isolate failures so that one slow component does not consume all system resources. Fallback mechanisms provide default responses when dependencies are unavailable. Monitoring and health checks are also part of resilience. Systems must detect failures early and respond automatically. In interviews, experienced developers are expected to explain that resilience is a design mindset. Spring Boot provides tools, but developers must design services assuming that failures will happen and plan accordingly. Next question, how do you design and handle distributed transactions in microservices? In microservices architecture, distributed transactions are challenging because each service owns its own database. Traditional database transactions cannot be used across multiple services without creating tight coupling and performance problems. Because of this, microservices avoid global transactions and instead use eventual consistency. The most common approach is to break a large business transaction into multiple local transactions, one per service. Each service completes its operation independently and publishes an event when it succeeds. Other services react to that event and perform their own actions. If a failure happens in one step, compensating actions are executed to undo previous steps. This approach ensures consistency over time rather than immediately. This design requires careful planning. Services must be idempotent so that repeated events do not cause duplicate actions. Error handling must be explicit, and retries must be safe. In interviews, experienced developers are expected to explain why traditional transactions do not work in microservices, how eventual consistency solves the problem, and what trade-offs are involved. Interviewers look for understanding of real-world failure scenarios, not textbook definitions. Next, how do you handle API versioning in Spring Boot microservices? API versioning is essential in microservices because services evolve over time while clients may not update immediately. Without versioning, a breaking change in one service can break multiple consumers and cause production outages. Versioning allows services to introduce changes safely while keeping older clients working. In Spring Boot microservices, versioning is usually handled at the API contract level. Each version represents a stable contract that clients can rely on. New versions are introduced when breaking changes are required. Old versions should continue to work until clients migrate. Deprecation strategies are important so clients know which APIs will be removed in the future. Versioning increases maintenance effort because multiple versions must be supported simultaneously. However, this cost is much lower than breaking production clients unexpectedly. In interviews, experienced developers are expected to explain why versioning is necessary, how it protects consumers, and how to manage multiple API versions without duplicating too much logic. This shows maturity in API design and long-term system thinking. Next question. How do you ensure observability in complex Spring Boot microservices systems? Observability means understanding what is happening inside a system by looking at its outputs. In microservices, a single user request may travel through many services. Without proper observability, debugging becomes extremely difficult. Observability is built on three pillars: logs, metrics, and traces. Logs capture detailed events, metrics show system behavior over time, and traces show how a request flows across services. Each microservice must log important actions with enough context to identify issues. Metrics help detect slow responses, high error rates, or resource exhaustion. Tracing connects requests across services so failures can be pinpointed quickly. Correlation identifiers are critical. Every request should carry an identifier, so logs and traces across services can be linked together. In interviews, experienced developers are expected to explain why observability is mandatory in microservices, how it helps reduce downtime, and how teams move from guessing problems to diagnosing them accurately in production. Next question. How do you design microservices for independent scalability? Independent scalability is one of the main reasons for adopting microservices. Each service should scale based on its own workload rather than the needs of the entire system. This requires services to be stateless and loosely coupled. State should not be stored in memory. Instead, shared state should be externalized so multiple instances can handle requests interchangeably. Services that handle heavy traffic should be able to scale without affecting others. This reduces infrastructure cost and improves system efficiency. Data access patterns also matter. Services should not share databases because that creates hidden coupling and prevents independent scaling. In interviews, experienced developers are expected to explain that scalability is not just adding more instances. It is about designing services so scaling one service does not force scaling of others. This demonstrates architectural thinking beyond basic Spring Boot usage. Next question. How do you handle configuration and feature rollout safely in microservices? In microservices, configuration changes happen frequently and must be handled carefully. Configuration should be externalized so services can change behavior without redeploying code. This allows faster fixes and safer operations. Feature rollout should be gradual. New functionality should not be enabled for all users at once. Instead, features can be enabled selectively and monitored for issues. If problems occur, features must be disabled quickly without redeploying services. This reduces downtime and risk. Configuration errors are one of the most common causes of production failures. Validation and clear separation between environments are critical. In interviews, experienced developers are expected to explain why safe rollout matters, how configuration is managed across environments, and how teams reduce risk when introducing changes in large microservices systems. This reflects real operational experience. Next question. Describe a common cascading failure scenario in microservices and how you debug it. A cascading failure happens when one failing microservice causes multiple dependent services to fail. For example, a downstream service becomes slow due to database issues. Upstream services continue sending requests and wait for responses. Their threads get blocked, thread pools become exhausted, and soon those services also start failing. From the outside, it may look like the entire system is down, even though the root cause is a single slow service. Debugging starts by checking system-wide symptoms. Response times increase, error rates spike, and thread pools show saturation. Logs often show timeout errors rather than clear failures. The next step is tracing requests across services. Traces usually reveal where delays are happening. Metrics help identify which service is consuming most time or resources. Once the root service is identified, the fix usually involves adding timeouts, limiting retries, and introducing circuit breakers. This prevents failures from spreading. In interviews, experienced developers are expected to explain not just what cascading failure is, but how they recognized it, isolated the root cause, and changed the system design to prevent it from happening again. This shows real production experience. Next, how do you debug high latency issues in Spring Boot microservices? High latency issues often appear gradually rather than as sudden failures. Users may report slow responses even though the system is technically up. CPU and memory may look normal, making the issue harder to diagnose. Debugging starts with identifying where time is being spent. Metrics help determine whether latency comes from the application, database, or external service calls. Distributed tracing is critical here. It shows how long each service and each operation takes during a request. Often, one slow database query or external API call dominates the response time. Logs are used to correlate slow requests with specific inputs or conditions. Sometimes, latency only happens for certain data sizes or edge cases. Common fixes include optimizing queries, adding caching, reducing payload size, and tuning thread pools. Sometimes the fix is architectural, such as switching synchronous calls to asynchronous processing. In interviews, experienced developers should explain how they move from symptoms to root cause and why guessing without data usually makes latency problems worse. Next question. Explain a production issue caused by misconfiguration and how you troubleshoot it. Misconfiguration is one of the most common causes of production incidents in microservices. A typical example is incorrect timeout, connection pool size, or memory configuration. The application may work fine in lower environments but fail under real production load. Symptoms can include frequent timeouts, connection errors, or unexpected restarts. Logs may show errors, but the real issue is configuration, not code. Debugging starts by reviewing recent changes. If code has not changed, configuration becomes the prime suspect. Comparing production configuration with staging or previous working versions often reveals the issue. Metrics help confirm whether resources are being exhausted. For example, connection pool metrics may show all connections in use, indicating misconfigured pool size. The fix usually involves correcting configuration values and redeploying or reloading configurations safely. Long-term fixes include validation, sensible defaults, and better environment parity. In interviews, this question tests whether candidates understand that many failures are operational, not coding mistakes, and how careful configuration management prevents outages. Next question. How do you debug memory leaks in Spring Boot microservices? Memory leaks are dangerous because they often appear slowly and worsen over time. A service may run fine initially, but gradually consume more memory until it crashes or becomes unresponsive. Restarting the service temporarily fixes the issue, but the problem returns. Debugging starts by observing memory metrics. A continuously increasing memory usage without release is a strong indicator of a leak. Garbage collection logs often show increased frequency without effective cleanup. Next, heap analysis is used to identify objects that are retained unexpectedly. Common causes include unbounded caches, static references, and listeners that are never removed. In microservices, memory leaks can also occur due to excessive object creation from high traffic or improper handling of large responses. Fixes include limiting cache size, cleaning up resources properly, and reviewing object lifecycle management. In interviews, experienced developers should explain that memory leaks are rarely obvious and require systematic observation, not trial and error fixes. Next, describe how you debug a production issue that you cannot reproduce locally. Some production issues cannot be reproduced in development environments due to scale, traffic patterns, or real user behavior. In such cases, debugging relies on observation rather than reproduction. Logs, metrics, and traces become the primary tools. The first step is narrowing down the conditions under which the issue occurs. This may involve identifying specific users, requests, or times when failures happen. Next, additional logging or diagnostics may be enabled temporarily but carefully to avoid performance impact. Feature flags are often used to isolate suspected code paths. If necessary, a controlled fix or workaround is applied to reduce impact while deeper analysis continues. The goal is to stabilize the system first, then fully understand the root cause. In interviews, experienced developers are expected to explain a calm, structured approach to debugging under uncertainty. This demonstrates maturity, responsibility, and real-world problem-solving skills.